Oui, c'est bon.
C'est bon, comme ça?
Oui, c'est bon.
OK. OK. Donc, merci beaucoup. Je vais donner la présentation en anglais. Je suis désolée pour ça. Mais d'abord, avant que je commence, so of course, I would like to wish Xavier a smooth recovery. Our thoughts are with him, and I'm stepping in today as announced earlier on. So we will hopefully have the pleasure to listen to Xavier's contribution very soon at another occasion. Now, what I would like to present today is a paper that in fact we were able to wrap up, I think, a couple of weeks ago and put online a couple of weeks ago. And similar to, the approach that Matthias took in his presentation, this is a topic that I've been talking about and exchanging thoughts with the team on a couple of occasions. I think I did the very first petit déjeuner or wiki meeting about the foundations of this topic. So I would like to get back to it, to the final paper that we put out, and I would like to give you a quick tour, a guided tour of what one can find in this paper. Right. So what are we going to talk about? I'm going to focus on non-life insurance pricing with frequency severity data. And I would like to explore what the potential added value can be of using neural network kind of techniques to build predictive models for frequency and severity data. And to give you to give credits to my co-authors. So I worked on this project with Freek, who is a colleague at the University of Leuven, and with Roel, who is a former colleague at the University of Leuven. The paper can be downloaded for now from arXiv, and I'm sure we can have a link via the website of the chair to the final paper, which is available on arXiv only since, like I said, 1 or 2 weeks. Now, what would I like to put forward by means of introduction? So in contrast to the contribution of Pierrot today, I'm going to assume that we're going to think about pricing, where we have historical data available on frequency severity data in the presence of covariates of risk factors. And then we know that typically we are going to explore certain predictive modeling tools to come up with a technical assessment of the pure premium, of the break-even premium on for a particular insurance product. So that's a bit the flow that I have in mind. And if we then reflect on which modeling tools come forward to do this kind of model building, to do this kind of analysis, well, I think the first go-to modeling tool would be the generalized linear model setting, where we can build a GLM for frequency data, a GLM for severity data, independent from each other, and combine these assessments into a technical tariff, into the pure premium. This is something that I've been working on, that multiple other people in the room or in the session have been working on as well. Now, what I would like to talk about is that, of course, next to these GLMs, we can explore other kinds of modeling tools, and machine learning techniques then, of course, come forward. And we've been working with the team on exploring, let's say, tree-based machine learning techniques for this purpose. So I have a few acronyms here referring to decision trees, the tree structures that Matthias also talked about, but he had other target variables in mind. Random forest, gradient boosting machines, methods to combine multiple trees into a more performing ensemble method, let's say. So this is something I've also presented at another occasion in one of the seminars. And today, for me, the what I actually want to go to is, what if we challenge the techniques that were mentioned so far, and what if we challenge them with the ideas of deep learning, right? But before getting there, I want to add one last step. Of course, these machine learning methods are less interpretable, less explainable compared to the more traditional statistical learning techniques, right? So in this contribution, we're also going to try to use the insights captured by more sophisticated learning methods, machine learning methods. We're going to try to use the insights captured by such methods to design then a more simple method, in this case called surrogate GLM, as a close approximation to the more sophisticated learning methods. So ultimately, the idea is here to put such a GLM into production, to base the tariff insights on the findings obtained with such a GLM, but to construct a GLM in a clever way, using interpretability techniques, using techniques to look under the hood of these sophisticated learners. So this is an idea that we've been working on in the paper that you see mentioned here at the bottom, and which we would like to extend to, okay, what if deep learning comes to, is one of these techniques to be looked into as well? What kind of findings, what kind of improvements are then possible? Now, when studying the literature for what other people have been doing on this topic, and this is really in the first axis of the project within the chair, so exploring techniques, learning techniques, AI techniques, exploring interpretability tools, and things like that. So we summarized, or we tried to summarize a selection of papers from recent actuarial literature, let's say, and we particularly listed the contributions of these papers along the following dimensions. So what do they do in terms of how to use categorical covariates, factor variables? What kind of models do the model architectures does the paper explore? On how many data sets do they sort of investigate or challenge their findings? What kind of applications do they have in mind? So do they focus on frequency modeling only, or frequency and severity? Do they put the two models, frequency, severity, together into a tariff structure? And what kind of interpretation tools are used in this contribution? So we try to summarize the literature a little bit like this. The list is not exhaustive, so probably we're missing a few papers here and there. But I think this is a nice, at least for me, it's a nice way to look at the contributions in the literature and to see, okay, what have other people been doing, and where do we try to step in with our work. Okay. So what we like to contribute is that we're gonna use neural networks here as the modeling tools. At the end of the day, we still aim to put, say, a GLM into production, or to construct a GLM as a close approximation inspired by the findings of these deep learning methods. And what else do we want to add with this particular paper? We want to do let's say a small benchmarking study using multiple data sets instead of just illustrating our techniques on a single data set. We want to explore, and this is a bit technical, but we want to explore different so-called embedding techniques. And an embedding technique in this literature is a way to sort of convert a categorical input feature, like for instance, postal code if you want, or type of the car or something like that. So to convert a categorical input variable into a numerical format, such that it can be used later on then in neural network kind of techniques. So we want to explore with different ways to do that. Yeah, you see that was also one of the dimensions in my overview over here. So we really wanted to learn there and see, okay, what are good state-of-the-art methods to use these categorical input variables in a deep learning setting. And then a third contribution or point that we want to emphasize in the paper is to use quite a variety of interpretation tools to look under the hood of these neural network models, these deep learning models. And that's very much, as Anani mentioned in the beginning of the seminar, and that's very much at the heart of Axis One. We're working with AI techniques and interpretation tools is very important. So this is in one slide what you can find in the paper. So I guess this is the most important slide from my presentation today. So we do frequency, severity, modeling on multiple data sets. We're going to challenge the GLMs and the tree-based learners that we worked with in the past. We're going to challenge them with deep learning structures. We put focus on how do you use categorical information in such deep learning methods by using different embedding techniques. And at the end of the day, we want to gain insight from those sophisticated learning methods. So we're going to use interpretation tools, and we're going to use these insights to design a GLM as a good approximation for what the deep learning methods find. Now I will use my remaining time to dive a little bit into the different steps and to show some findings that you can then read about in a very detailed way in the paper. But first of all, whereas in previous work, we always tried, to explore our techniques on a single data set. So for now, we said, no, we want to collect a few open data sets from the actuarial literature, and we want to make sure that we do a bit of a benchmark study so that we can also illustrate the techniques and the findings across multiple data sets. And so the ones we have been working with, and Christophe knows about these data sets very well. I think it's thanks to the open source work of Christophe Duton as well that we have access to these data sets to work with in the literature. But here you see we have an Australian one, a Belgian one, a French one, a Norwegian one. You can read about the dimensionalities of the data sets, the type of covariates in the number of covariates, etc. Yeah, so you will see all our findings illustrated on all these data sets. Then briefly, what kind of modeling architecture, so deep learning architectures do we have in mind? We're going to set up a few model structures. First one is very traditional in this literature, a typical feed-forward neural network, an artificial neural network. So I remember we go back, I think, almost 2 years or something. I gave a seminar about, the foundations of this type of modeling structure. So today I'm going to be very brief. So you have some input information here colored in green in the input layer. You have a few layers in this structure with certain dimensions. And at the end of the day, you deliver a prediction in the output layer. And so the kind of predictions I have in mind here is expected prediction for frequency and a prediction for the severity, taking into account exposure, taking into account the characteristics of the policyholder, and so on and so forth. So when training such a network, we're going to train one network for the frequency data. We're going to use the Poisson deviance, so kind of Poisson distributional assumption there as the loss function to train such a network. And we're going to train another network for severity data, right? And there we're going to use the gamma deviance or the gamma distributional assumption to train the weights, the bias terms in this neural network specification. Yeah, so that can be done. You can read about all the elements that we allow to tune on. You can read about the details in the paper. Now, recently in the actuarial literature, another clever idea has been suggested by Professor Wüthrich and colleagues, and that's the idea of a combined actuarial neural network. But we're going to say that we're going to sort of use the network to build a correction, if you want, on top of a kind of baseline prediction established by another, preferred modeling techniques. And typically you could see this baseline prediction as the prediction that you obtain with a GLM, for instance, using some covariates, of which you know that they're going to matter in the prediction of the frequency or the severity. Yeah, so here you assume that there is some kind of baseline assessment, the y hat in, the initial model input, and you train the neural network to build a correction on top of this baseline input. Now, the way how that has been done in the literature is what we call in the paper with a fixed structure. So in that case, your final prediction will look like this. So if you are thinking of an application that at the end of the day, the y-hat should be positive, you have an exponential function here, you have the neural network correction, and then plus the, well, in this case, the logarithm of the baseline prediction. Now, we allow in the paper to explore sort of a little tweak, a twisted version of this CAN, if you want, and we call it the flexible CAN, in the sense that we allow to train weights, a weight to put on the neural network correction, a weight to put on the baseline correction, a bias term. So it just gives a bit of extra flexibility in coming up with this, well, with this kind of structure. So that's the second, well, deep learning architecture models that we explore in the paper. I would maybe should emphasize, and that's also, I think, well described in the introduction of our paper, that this kind of idea has also been explored in the computer science literature, where people, when analyzing tabular data, so typical data sets where you have observations in rows, and then you have a number of columns with covariates, where people have tried to analyze tabular data with neural network structures. They saw most value in this kind of constructions, like first establishing a baseline assessment for that tabular data set using a more traditional learning technique, and then building a correction with a neural network structure on top of that to refine those predictions. Now, so that's in terms of the architectures, the model architectures that we explore. Of course, if you want to use input data in such neural network models, there are a few pre-processing steps that you have to go through. I'm not going to talk about all of them, but I'm going to focus on what we do for the categorical input variables, because that, I think, is something where we try to explore a recent suggestion by Professor Lucas de Long from Warsaw in a recent paper, and where the idea is to find this kind of embedding for the categorical input variables. So what is an embedding? Once again, it's a way to do a sort of numerical conversion of your original categorical input data, such that you can use that numerical encoding later on in the neural network structure. And what we're going to do is we're going to rely on neural networks of a specific type called autoencoder neural networks, where the idea is here in green you have the categorical input variables, and in this network structure you're going to learn this encoding here in the middle layer, and then from the encoding you can decode the information, and you find then here some kind of, well, close approximation of the original information. So here we're particularly interested in using this idea of the autoencoder neural networks as a kind of pre-training step to learn this representation of the categorical information. So we're interested in capturing this middle layer here and to plug it in then in our neural networks that we want to train later on. Yeah, so we want to train this autoencoder and use it as a lower dimensional numerical representation of the original categorical input variables. So what we're going to do is we're going to focus on pre-training these neurons in blue, and then plug them, as I said, plug them into our neural network structures and learn or train the neural network with this encoded information further on. Yeah, so this gives a bit, gives a summary of the whole procedure then. So we are interested in learning this encoding up front, but then we allow the network to sort of refine it further on by plugging it here in the structure. Now, what is the good thing? that you can train this autoencoder across, without making a distinction between the frequency and the severity data set. So you can sort of learn this representation across the frequency and the severity data set. So, and you can plug it in then afterwards in the neural network model for frequency, but as well in the neural network model for severity. So that's what I had over here. It allows for cross effects. It's unsupervised learning. So you can train the autoencoder on your complete training data set and using the learned encoding then later on for both your frequency and severity. So we'll try to find some, well, to explore if there's some potential added value from there as well. So that is in a nutshell the kind of techniques we try to explore. And yeah, I want to give you a quick tour across the findings and jump to some conclusions. Well, as you can imagine, first of all, there are quite a few things that you need to tune here. So you need to tune the number of layers, the activation functions, the number of neurons, and so on and so forth. So maybe an interesting thing to mention here is that we explore a technique that is called a random grid search strategy. So we basically put a grid together based on all the tuning parameters and the range that we want to explore. And then we're just randomly going to draw certain candidate tuning parameter vectors from this grid and explore or train the whole neural network with these chosen tuning parameter vectors. Yeah, so that's just to get around the dimensionality of the possible tuning parameters here and the possible values one wants to explore as tuning parameters. We're going to do some out-of-sample evaluation. I think I'm going to skip that and just try to show you some results here, because of course the initial question was, yeah, is there any value in using these sophisticated models when building models for frequency for severity data? So I can disclose that in our opinion and based on our benchmark study here, the added value in terms of improvements in predictive performance is rather small, and that is in fact in line with what other fields, other literatures have also found when analyzing tabular kind of data with deep learning structures. So you see some improvements. If you look at the Poisson deviance, you see some improvements if you work with those CAN models with a gradient boosting machine baseline input. So you see that these typically lead across our experiments to the best performance in class, but that the improvements are definitely not huge and not very large compared to what other techniques would find. What we do conclude is that if you stick to a simple feed-forward neural network, so without giving it an initial baseline input, that then the neural network really struggles to reach good performances and also to capture well, meaningful effects of the input values. Yeah, so the CAN structures are definitely a better idea to explore than the pure neural network strategies. We have the same for severity. So here the results are more mixed. We know that severity modeling is typically way harder to find a consistent view there, and also to build meaningful predictive models for severity data. We explored with the autoencoders, and we tried to visualize their effect as well compared to just using a one-hot encoding strategy. So here we conclude that the biggest improvements are to be found in the severity data. So that is perhaps more probably due to the idea that we can train the autoencoder on the large data set and then enrich the severity data analysis with the findings of this autoencoder. We looked at quite a few interpretation tools, as mentioned. So we looked at the variable importance, so screening which variables matter the most in improving our loss function when training the neural network. So the findings there are pretty consistent for the frequency models, but more scattered for the severity models. I'm going to be a bit fast here, but you can find all the details there in the paper. And then insightful is that if you look at an interpretation tool called the partial dependence plot, and in this case, we're looking at frequency modeling. So we're looking at the expected frequency per unit of exposure, but as a function of the policyholder's age. So you see that the GBM in light blue and also the GAN structure is able to find their pretty nuanced view of this policyholder's effect on the expected claim frequency. But if you there just use a feed-forward neural network as is, without giving it that baseline input put together with another predictive modeling technique, then it really struggles to find some relevant insights there. Yeah, so that is definitely a finding of using or putting this benchmark study together, that the use of a feed-forward neural network without giving it that specific baseline input, that is not a good idea for frequency and severity modeling in insurance data sets. I think I'm running out of time, so I just want to conclude with saying we didn't implement that whole idea of then building a GLM as a surrogate model for the deep learning structures. So the idea is that you start with a black box model, in our case, a neural network, deep learning structure. You capture model insights using partial dependence plots, among others. You apply a certain clustering technique to then build a binning of the covariates, a segmentation of the input feature space. And then if you have all the covariates in this format, you can fit a GLM, and the GLM is then constructed as a surrogate model for the original black box. So that's something we really implemented here in the paper for all the different for the different data sets and for the different deep learning architectures. So where you start with the covariates as they are, and at the end of the day, get a segmented view of these, or a binned view of these covariates. We then also explored in terms of out-of-sample accuracy, predictive accuracy, how close does that surrogate GLM gets to, for instance, a GLM put together with different techniques or the deep learning structures. You can find these comparisons in the paper. So let me jump to some conclusions, and I think I'm put in a slide with a picture that takes time to load, and which kind of prevents me now from moving to the final slides. We did put in a comparison in terms of risk differentiation across the different techniques and the different data sets explored, and that's what it's trying to load here. Okay, so sorry for the hiccup, but my image included is apparently a bit too large to display properly. So let me talk you through the conclusions and then just stop. So based on this benchmark study, we must conclude honestly that the deep learning structures, they bring some but very limited added value, in our opinion, to improve in terms of predictive performance on frequency severity data sets. If you want to use them to enrich your GLMs, that can be done by relying on these interpretation tools for sophisticated learning methods, and then translating these insights into your deep learning structures. And that is a way then to put so-called surrogate GLMs together based on the insights captured by the deep learning methods. And they come up with a predictive power that is close to the one of the original deep learning strategies. We did put in, of course, the list of references, and I want to show you the final slide. That's going to work. on my presentation, because I put in 2 QR codes where you can find the paper and also the notebooks to replicate the experiments in the paper. So let me try to show you that as the final slide for this morning. Meantime, I can give the floor back to Alani for the Q&A, and I hope that the QR codes will show up. Here they are. So if you want to check out the paper on the archive, if you want to see the code on GitHub, these are the links, and you can share that afterwards, of course. Thank you.
Ok, merci.